Welcome back. In a recent video, we discussed how addresses are important. Devices need them so they know where to send their data. IP addressing is a good example of this. Not only does it include the address of the device, but the address of the network that the device is in. That means, with one simple address, we can find a device on our local network or on the other side of the world. IP addresses come in two different flavors. These are called IPv4 and IPv6, and they look quite different. IPv6 is newer, but IPv4 is still more common, so we're going to focus our attention entirely on IPv4 for now. Firstly, this is what an IP address looks like. It's 4 numbers separated by dots. Each of these numbers is called an octet, as each number is an 8-bit value. We break it up into 4 separate octets to make it easier for us humans. Oh, and if you're having trouble remembering what an octet is, think of an octopus. An octopus has 8 tentacles, an octet has 8 bits. 8 bits means that these numbers can range from 0 to 255. That means that an IP address starts at 0.0.0.0 and ends at 255.255.255.255. We call a range of addresses the IP space. Straight away, you can see that knowing how binary works is important for IP addressing. If you don't know binary, or if you need a refresher, I have a video to help. I'll add it to the description. IP addresses are actually 2 addresses in one. The IP address is the address of the device, but it's also the address of the network that the device is in. 2 addresses in one? How is this possible? Let's take a look at this sample IP address here, 172.16.0.1. The first part, 172.16, refers to the network. The second part, 0.1, is the host address. Don't worry, I'll get to explaining how we know the difference between the two soon. All the hosts here that start with 172.16 are in the same network. If we add more hosts, and the IP addresses start with 172.17, then this is a different network. If hosts in different IP networks need to communicate, then there will need to be a router between them. You're probably wondering, is it always the first half of the address that represents the network? Short answer, no. How then do we know which part of the IP address is the network and which part is the host? The answer to this question, strangely, has changed over time. So let's start back at the beginning and we'll work along from there. When the Internet Protocol was first created, the first octet always represented the network, and the following 3 octets were used for hosts. The largest value that we can get out of a single octet is 255. That means that there was only room for 255 different networks. On the other hand, 3 octets meant that there could be over 16 million host IPs in each network. This sounds a little unbalanced, but in the beginning the internet was not international and there were only a few organizations using it. But as the internet started to grow, it became obvious that this wouldn't work for very long. 255 networks just wasn't enough. So, back in 1981, a new method was introduced. This broke the entire IP space into 5 classes. That's Class A through to E. Class A, B, and C were used to address devices. Class D is for multicast, and we'll touch on that a little in the next video. Class E is reserved for special purposes. So Class A, B, and C are the ones we need to think about right now. There are a small number of Class A networks, but each network supports a large number of hosts. Class A works a bit like the old method. The first octet is the network, and the remaining 3 octets are for hosts. However, the first bit of the network is always 0. That leaves 7 bits for us to allocate to our networks. That means there are 128 Class A networks, with more than 16 million possible host IPs per network. The Class A address space then is 0.0.0.0 through to 127.0.0.0. There is a small catch with this though. Networks starting with 0 and 127 are reserved. So the usable Class A space is really 1.0.0.0 to 126.0.0.0. Class B networks are used for a medium number of hosts. The first 2 octets are used for the network, and the second 2 are used for host addresses. The first 2 bits of the network are always 10, which leaves 14 bits, or 16,384 possible networks. Each network can have over 65,000 hosts. The total Class B IP space is from 128.0.0.0 to 191.255.0.0. Class C are small networks, but there are a lot of them. The first 3 octets are just for the network. The first 3 bits are always 110, leaving 21 network bits, or a little over 2 million networks. With only 1 octet left though, we can have only 256 host IPs per Class C network. The address space ranges from 192.0.0.0 to 223.255.255.0. So, to summarize, Class A uses 1 octet minus 1 bit for networks. Class B uses 2 octets minus 2 bits. And finally, Class C uses 3 octets minus 3 bits. Addresses outside of this are classes D and E, which are reserved for special uses. If you're the kind of person that likes the math, we can show this as an equation. The number of networks is 2 to the power of n. N is the number of network bits. So Class B has 14 network bits. 2 to the power of 14 is 16,384. The same is true for hosts. Class B has 16 bits for hosts. 2 to the power of 16 is about 65,000. Ready for some practice? Take a look at these IP addresses. Which classes are they in? Time to look at an example. If device 172.16.0.1 wants to send a packet to 172.16.0.2, it starts by looking at the first few bits of the destination IP address. As the first 2 bits are 10, it knows that this is a Class B address. It can then assume that the first 2 octets are the network and the last 2 are the host. It sees that the destination network is 172.16, which is the same as its own. As they're in the same network, it can send traffic directly to the destination. Now, what if it wants to send a packet to 172.17.0.1? It does the same thing, and it determines that the destination is on the 172.17 network. This is different to its own network, so it can't send traffic directly. It needs to send traffic to a router first. Take the practice session from before a step further. Tell me which part of each address is the host address. As the internet started to grow, we started using up IP addresses faster and faster, and we started running low on IP addresses again. So in 1993, yet another new method was introduced. It is called Classless Inter-Domain Routing, or CIDR. Previously, we could identify IP address class by looking at the first few bits. Knowing the class, we then knew which parts of the IP were for the network and which parts were for the host. But now we throw all that away and we introduce something new, the subnet mask. The subnet mask is also made up of 4 octets. This lines up with the IP address bit for bit. The bits set to 1 tell us which part of the IP address is the network. The 0 bits are used for hosts. It's important to notice that all the 1s go on the left and all the 0s go on the right. We never mix up the 1s and 0s in a subnet mask. Take a Class A address for an example. We know 8 bits are used in the network. So the subnet mask would look like this. 8 1 bits for the network, the remaining 24 bits set to 0 for hosts. A Class B address follows the same rules. 16 bits for the network, set to 1, and the host bits set to 0. And finally Class C. Well, you get the idea by now. Is this making sense so far? The subnet mask tells us which part of the IP is for the network and which part is for the hosts. But this hasn't really addressed our original problem yet, has it? So far, we've just seen a different way to show Class A, B, and C addresses. So far, we haven't seen anything on how to save IP addresses. The real power of CIDR is the ability to break a large network into small ones. We call this subnetting. Let's say that you have the classful network of 172.16.0.0. This would have the subnet mask of 255.255.0.0. This allows for about 65,000 hosts. That's a lot of hosts. That might be fine if we have one massive office, but what if we have several smaller offices? Do we want to allocate 65,000 IPs to each office? That seems like overkill to me. So instead, what we can do is we can break the Class B network using our subnet mask. We may decide to use 255.255.255.0 instead. Now, our large office network has been broken into 256 different subnets. Why 256? Well, our subnet mask is now using an additional 8 bits for the network. The largest 8-bit value is 256. Now we can allocate 256 host IPs per network, which is far more reasonable when we have a few small offices. If we want to communicate between our subnets, just like before, we will need a router. Let me take a moment to make sure that I'm clear on this. Devices in the same subnet must be in the same IP network. If not, they will not be able to communicate. Likewise, if devices in the same subnet are separated by a router, they will also not be able to communicate. I'd like to challenge you to think this through for yourself. Take the 172.16.0.0 network with a subnet mask of 255.255.0.0. If we broke that network up by using the subnet mask of 255.255.240.0, how many subnets do we have? How many host IPs per subnet are there? If you're taking notes, you've probably noticed that it's a pain to write down the subnet masks all the time. To make things simple, we have what's known as CIDR notation. Take 172.16.1.0/24 as an example. The /24 is the subnet mask written in CIDR notation. This means that the first 24 bits of the subnet mask are turned on. It's that easy. We will be using CIDR notation more and more from here on, so try to get more comfortable with it. See if you understand by testing yourself with this example. We have two /24 networks. These are joined together by a small /30 network. A device in network A is unable to communicate with a device in network B. Why are they unable to communicate? Classful is an older method of networking, and subnetting is newer. So why are we even talking about classful networking? Hasn't it been replaced? Yes, it has been replaced. But for one, if you're doing an exam, you may still find exam questions that refer to classful addressing. We also have some remnants of classes in everyday networking. Think of when you set an IP address in Windows, for example. If you configure an IP of 10.8.6.2, Windows will automatically give you the subnet 255.0.0.0. It's assuming classful networking. And while we're mostly classless now, a lot of people tend to think of subnetting as starting with a classful network and breaking it up from there, which is not always strictly true. Sometimes we may have a few small networks and we decide to join them together. This is called supernetting. For example, we may have 192.168.0.0/24 and 192.168.1.0/24. If we want, we can join these into a single network, 192.168.0.0/23. In my opinion, we shouldn't really worry about classful networks in the real world. Use subnetting all the way. But what do you think? Tell me if you agree or disagree in the comments. I would love to hear your opinion. Join me in the next video and we'll dive deeper into IP addressing concepts.